Thank you again, viewers, for joining to the lesson. We are going to cover on the second part of vectors, that is vectors in three-dimensional coordinates. And the good news here is that all the rules for 2D vectors apply in the same way for three-dimensional coordinate vectors. And now, in three-dimensional coordinate vectors, we have the following. We are going to look at the 3D coordinate system, whereby we can say that world points in space can be located using the three coordinate system. For example, air traffic controllers find the location of a plane by its height and grid reference. See this. Wow, that is the plane. Now, the controllers would want to find the location of this aeroplane. And of course, they are going to use the three coordinate system method, whereby they are going to determine the height from the ground and the grid reference. So this is what we are talking about. We have the x coordinate, we have the y coordinate, and the z coordinate. So that is headed to x. Again, this one is headed to y, and then this is headed to z, which shows the height to the plane, or rather the height from the ground to where the plane is. But now x and y are on the ground. Of course, x is for the latitude, and then y is for the longitude. So we have the coordinate system, 3D coordinate system of this plane to be x, y, z. So that is the concept of vectors in three-dimensional coordinate system. Now, we have that 3D vectors are defined by three components. For example, the velocity of an aircraft taking off can be illustrated by the vector v. So we have from the origin to the x coordinate, we have that measurement, let's say 7, and then we have this one represents y coordinate, so it is 3 units. And then lastly, we have the z coordinate, which is 2 units from the ground. So that means the point where we have that object, it will be of coordinate 732. 732. So of course, up to x we have 7 units, and then we have again 3 units, and finally 2 units. So let's now start with the unit vector in the 3D concept. So any vector can be represented in terms of the I, j, and k, where I, j, and k are unit vectors in the x, y, and z directions. So we have in the x coordinate, it will take I, then y coordinate takes j, and finally z coordinate takes k. So that means that I occupies the first position, and so in column vector, it can be written as 1, 0, 0. That is in the 3-coordinate system. And then J, vector J, you need to understand that J occupies the second position, and so it will be 0, 1, 0. And finally, K occupies the third position, and now the coordinate is 0, 0, 1. So that is unit vectors. And so we also have that unit vectors appears to take these 3 letters I, J, and K, which we have also used. So we are going to take an example of now the measurement. So we have X has been measured to be around 7 units, Y 3 units, and Z is 2 units. So this means that the coordinate of X, Y, Z will be, in terms of I, J, and K, will be 7, 3, 2. 7, 3, 2 because of that point. And so vector V, which was the velocity of an aircraft, vector V can be given as 7I, or the 7 vector I, plus 3 vector J, plus 2 vector K. So if you want to find the coordinate of vector V, then it is 7, 3, 2 in column vectors. So you don't have to write, in column vectors we don't write I, J, K. We just take the numbers. So it's going to be in terms of X, Y, Z. So for X is 7, for Y is 3, and for Z is 2. So we have vector V is 7, 3, 2. Now let's look at the magnitude of a vector. And a vector's magnitude, that is length, is represented by magnitude or modulus or length or distance of vector V. So all those words, they mean the same thing for magnitude. Now we have the diagram here below. A 3D vector's magnitude is calculated using Pythagoras theorem. And 3D because we have X, Y, and Z coordinates. And so we are going, this means that vector V, for vector V, the magnitude of vector V is the square root of X squared plus Y squared plus Z squared. So this is going to mean for X we have 3, then Y represent 2, Y is represented by 2, and Z represented by 1. So we have that the modulus of vector V is equal to a square root of 3 squared plus 2 squared plus 1 squared. Okay, so we have that modulus for vector V will be root 14. Root 14 is a surd, and I think this cannot be simplified further. It remains to be root 14. So let's move to addition of vectors. And under addition of vectors, we let vector U to be 3, 4, 1 and vector V to be 2, negative 5, 2. Therefore, we have vector U plus vector V we will get 3, 4, 1 plus 2, negative 5, 2. And now the answer is 5, negative 1, 3. In general, on addition of vectors, we have that for vectors u and vector v, if vector u is equal to ABC and vector v is equal to DEF, then we have that vector u plus vector v is equal to ABC plus DEF, and so we are going to add the components. So the components in the first part is A plus D, and then we have B plus E, and then C plus F. So that is on addition of vectors. Now moving to negative vector. So here we have that AB, vector AB, and again vector BA. So the direction are not the same in this diagram, and it is intentional. So we have vector BA is the negative of vector AB. It is the reverse or negative of vector AB. Now for any vector u, we have that vector AB is represented by vector u, and vector BA is represented by vector negative u, because it's the reverse of vector AB. And so that would mean vector u plus minus vector u, you get 0. That is vector 0 written as such. Now if vector u is equal to ABC, then it means that vector negative u, because it is the reverse or negative vector to u, it will be written as or given by negative A, negative B, and negative C. So on the other part, on subtraction of vectors. So in this part we are going to let vector A to be 6, 5, 3 and vector B to be 2, 4, 2. Therefore, we can now subtract vector A, vector B from vector A. So vector A minus vector B. This will give us 6, 5, 3 minus 2, 4, 2. And now this is giving us 4, 1, 1. We are just subtracting the corresponding elements. Subtract the corresponding elements. Now we also have that for vector u and v, if vector u is equal to ABC and vector v is equal to DEF, then we have that vector u minus vector v is equal to ABC minus DEF. And now we do the same for addition by subtracting the corresponding elements. So A minus D. We also have B minus E and C minus F. Now the next part of this lesson is multiplication by a scalar. Multiplication of a vector by a scalar, whereby a scalar can be a number or any letter. Now we have, if a vector v is given as x, y, z, then vector v is given as kv, ky, and kz. You know, we did this in vectors in actually the first part of vectors, the two-dimensional coordinate vectors. And now the procedure is very simple. You just have to multiply the bracket by a scalar. So this gives us the vector kv, or k vector v is parallel to vector v, and the only difference is in the size. And now we have that, and if vector u is equal to k vector v, then vector u is parallel to vector v. That is correct. Conversely, if vector u is parallel to vector v, then vector u is k vector v. K vector v. So let's now have to solve this. Show that the two vectors are parallel. So we have vector w given by the coordinates 6, 9, 12, and then vector z given as 12, 18, and 24. Now if vector z is equal to k vector w, then this means that vector z is parallel to vector w. That is correct. And now we are going to find the value of k, that is the scalar. Because now if we have vector z is equal to k vector w, for example, we have 12 is equal to 6k, then it means the constant there is going to be a 2. Again, if you work out 18 is equal to 9k, then the value of k is 2. And finally, we have 24 is equal to 12k, then the value of k is 2. Now it is right to say that vector z is equal to 12, 18, 24, then equal to 2 into 6, 9, 12. So that means that the value of k has been taken care of. Now, this implies that vector z is equal to 2 vector w. Now on the position vectors, the position vector of a 3D point A is OA, usually written as vector A in small capital. And now this is summarized as vector OA, is equal to vector small a equal to 3, 2, 1. And that is the coordinate for the position vector of A. Again, if we have R is given by the coordinates 2, negative 5, 1, and S is given by 4, 1, negative 3, then vector RS is equal to vector S minus vector R. Vector S minus vector R. So you start with the S and then the other one, which is R. So that means we are substituting. We substitute because now we have the coordinates. So we have 4, 1, negative 3 minus 2, negative 5, 1, and so you'll get 2, 6, negative 4. Okay, let's now, as we end to close this lesson, let's do the ratio theorem. So we will say something on the ratio theorem, because now you realize that the ratio theorem, the only thing that's going to, I think with the ratio theorem there is nothing which is going to change. So summarizing in the summary of the ratio theorem, we have that a line AB with point P dividing the line internally, and so AP is M and PB given as N with the whole length M plus N. And so we have that if P is a position vector of the point P that divides AB in the ratio M to N, then we have that vector P, that is the vector for the position vector OP. So we have vector P is equal to N over M plus N of vector A plus M over m plus n of vector b.